Welcome to this lecture on insertion into binary search trees. We're going to go through an overview of how to do insertion, and we'll talk about a recursive implementation of that function, and we'll do some analysis, and we'll talk about dealing with duplicates. To insert into a binary search tree is fairly straightforward. We already know how to search for a node or for a value x, and we can do that because we need to know where the place to insert is. So we search for X, and we can do that iteratively or recursively. If we find X in the tree already, we stop and do not insert. And remember, that's by convention that we don't insert a duplicate into the tree. We'll talk more about that later. Otherwise, if we have found the position where X should be, but it's not there, we create a new node with the data containing the data X, and we'll attach the new node as a leaf. And it must be a leaf because we have reached a point where we could not go any further into the tree, and the node that we're searching for is not there. So if we're looking to insert, say, the value 45 into this tree, or let's say 35, I would start by searching for 35, right? Go left, right, and then I would want to go right again, but there's a null pointer right here, right? So I can't find 35, so it's not there. So I would create a new node, 35, and then I would attach it as a leaf, as the right child of 30. So some things to be aware of. What if the tree is empty? Well, the tree is empty if the root is null, and in that case, the node that we're inserting just becomes the root. Which parent should X have? If X is the node that we're inserting or the value that we're inserting, which becomes a new node, then of course it should have the parent of the last node before we reached a null pointer. Its parent is the last node in our search before we reached a null pointer. And should X be the left or right child of its parent? Well, it depends on whether it's greater than or less than its parent. Okay, so let's look at a recursive implementation of insertion. So here, again, we've broken up the function into two portions, the BST portion, which kicks off the recursion, and the recursive part inside the node. So inserting into a BST, we say if the root exists, then recursively insert and push all the work into this function. Otherwise, we simply create a new node for the root. And if we're inserting into, if we call insert on a node, we're given the data that we want to insert, and we do the same sort of thing where we're searching. If X is less than data and the left exists, then recursively insert on the left. Otherwise, what happened? Well, if X is less than data, suppose we're talking about inserting 35, right? Or let's say 25. So suppose we've gotten here. So 25 is less than 30, but there is no left pointer. Well, there's a left pointer, but it's null for 30. So we're going to make left equal to a new node here. Okay, that's what this line right here does. It says if the current node is 30, that's this. Okay, if I've gotten this far into my search, into my recursive search, if 25 is less than 30, yes it is. Do I have a left pointer? No, I do not. So set left equal to a new node, which we create right here. Otherwise, we do the right-hand case. If data is less than X, so X is greater than data, and if the right node exists, recurse, otherwise create a new node, okay? And what happens if this is not true and this is not true? So in other words, X is not less than data and data is not less than X. Then they are equal, in which case there's no else here. We just don't do anything, right? That's where we say, don't insert this. We've searched for the thing that we want to insert. We found it in the tree, so we're not going to insert anything. It does nothing at that point. Okay. So the analysis of this function is that most of the work is in finding the position to insert, right? Once we find the position to insert, then the only thing that's left is to create the node, which we can allocate on the heap, right? And that's just creating one node. and then attaching it to the tree, which is setting the parent's pointer to point to that new node. Those are two things that we have to do, which is constant time. Okay, so all of the work, almost all of the work, is in finding the position where we want to do the insertion. So the running time for insert into a tree with n nodes is the same as it was for searching. It's linear time for an unbalanced BST in the worst case, and it's log n for a balanced BST in the worst case. Okay, now let's talk about duplicates. Usually, binary search trees do not allow duplicates. As we saw in the code, if a duplicate is inserted, it's silently ignored. And this is just a convention. We could change it if we wanted to, but how could we change it? Well, here's at least two methods of doing that. One way is we could keep extra copies at each node with something like a vector. So every time something gets inserted, if it's a duplicate, we just add it to the vector of those things that we're keeping at that node. And this is useful if the duplicates are not necessarily exactly identical. For example, we know that we detect where something should go based on operator less than. But what if the operator less than is only based on partial information? Like you're trying to create a BST which orders people by first name and only first name. Then everyone with the name Susie would go to the same node, and that same node would have all the Susies, even though those are different people, right? So the question is really, does the operator less than take into account all the information needed for completely disambiguating different objects, or is it only a method of sort of quickly finding people named Susie or George or Fred or whatever? Okay. The other method that we could have for keeping duplicates is we could keep a counter of the duplicates with an integer. And this, of course, is more memory efficient because what we would do is anytime we saw a duplicate item, we would simply increment the item's counter at that node. And whenever we removed it, we would decrement the counter at that node. And if that counter goes to 0, then we would actually extract that node from the tree. And this is good if the operator less than reflects complete information about which nodes are really less than or really greater than each other, because the operator less than is based on complete information in the object. Okay, so those are two ways you could deal with duplicates if you wanted to maintain duplicates, allow duplicates in the tree. But again, by convention, usually we don't do this.